Hi, I'm Todd Bowers, and this is the Rutherford and Bohr model of the atom. Now this video is going to address two of the major contributors to our modern understanding of the atom and their theories, as well as some demonstrations and applications of their work. Rutherford's experiment consisted of passing alpha particles, essentially just positively charged helium nucleuses, through a thin foil to determine how these positive particles would interact with a lattice of atoms. The prominent model of the atom at the time was the plum pudding model, with protons symbolized by the orange pudding you see here, and the electrons represented by the little blue plums seen scattered throughout. Using this model, you would predict that the alpha particles would simply pass through the foil, as you can see here. However, the results that Rutherford recorded were significantly different, as you'll see as I set up the next demonstration. Rutherford was forced to come up with a new theory, as a significant number of particles were deflected from their trajectory and some even bounced back, as you can see here. You can even see the yellow nucleuses repelling the purple alpha particles, and in some instances you can even see them bouncing back towards the source of the alpha particles. This phenomenon proved that most of the atom is empty space, with the majority of the mass centralized in an extremely dense nucleus. A dense nucleus would have the mass and charge necessary to repel these alpha particles, so Rutherford concluded that most of the mass was concentrated in a compact nucleus consisting of protons and neutrons, with electrons circling almost like planets in a solar system orbiting the sun. Rutherford's model was the beginning of a huge change of thought in regard to atomic theory. However, it still wasn't able to explain much of the phenomenon seen in the day. Niels Bohr was a brilliant theoretical physicist that combined theories put forth by multiple scientists of the day and came to the conclusion that elements emitted unique spectra because of their electron configurations. Working with hydrogen atoms, he refined the equation used to interpret atomic spectra in order to prove that electrons can only be excited or launched to specific orbitals by the packets of energy they absorb, and that those quantified packets of energy are then released in the form of light, or photons, as the electrons drop back to its ground state, thus adding the orbitals to the existing planetary model suggested by Rutherford. There's kind of a lot going on in this demonstration, but if you focus on the blue electron circling the red nucleus at the center, you'll see it excited by a pink photon of light. The electron jumps from its ground state to the fifth orbital on the left-hand side. As you follow it around its orbital, you'll notice it dropping back down to its ground state, releasing light with each drop. First two black photons, then a red, and finally a pink photon, ending up at its ground state orbital until it gets excited again. Fortunately, we have discovered more information about atoms since the early 1900s because the Bohr model did have its shortcomings, despite being groundbreaking at its time. Probably the most detrimental of which was that his theory only applies to single electron atoms, although organic chemistry would be much less intense if we only knew in-depth information about hydrogen. Since Bohr's time, we've also discovered that orbitals are more like clouds of probability than distinct lines, which adds a whole 2 dimensions to things. There are other faults as well, but at the end of the day, the contributions of Rutherford and Bohr set the stage for everything that we now know about the basic building blocks of the universe. Now here's a problem working through Bohr's theory. So this problem is running through an application of Bohr's theory of the hydrogen atom. It's asking us to show that the first line in the Lyman series is UV radiation by calculating that first line's wavelength. So in order to do that, we're going to use Bohr's equation, which is 1 over wavelength equal to Rydberg's constant multiplied by 1 over n squared final minus 1 over n squared initial. And that n initial is going to equal the orbital in which the electron starts. And n final is the orbital in which the electron is ending up. And for Lyman's series, we know that n final is always going to be 1, so that ground state orbital. The n initial for this one, since it's the first line, in the Lyman series, we know that that is going to be in the second orbital. So the electron starts in the second orbital, drops down to the first orbital, and should release a wavelength of light that is in the UV region. So from there, we're going to find the Rydberg constant, which we know to be 1.097 times 10 to the 7th over meters, or meters inverse, whichever you want to write. And from there, it's just plugging in and working through the problem. Oh, forgot a bit there. And that ends up being 0.75, so that turns out to be 0.25. 1 minus 0.25 is 0.75. And then 1 over wavelength is going to equal 8.2275 times 10 to the negative 6, or 10 to the 6th. And at that point, we take the inverse of both sides, which will give us wavelength. And wavelength is equal to 1.215 times 10 to the negative 7th meters. So we can reference a UV chart and find that UV light ranges from 3.8 times 10 to the negative 7 to 1.0 times 10 to the negative 8 meters. Luckily, that falls into the right wavelength, so we're set. Thanks for watching. Make sure to like and subscribe for more content.